One last cool example of a family of distributions that we should explore before we get to normal distributions are what we call the exponential distributions. So they're actually based on a Poisson model. If you remember in the last chapter, we were talking about Poisson distributions. So one classic example for this is in credit risk modeling. So with the credit model as it currently exists, right? So you, as a consumer, may apply for a credit card, may be approved to use those funds and then pay them back along with some calculated interest. Now, on the other side of that, you have the creditors, who are, banks and the credit card companies, who have to assess the risk in giving you credit. In other words, because it's possible for a debtor, so somebody who owes this debt, this credit card debt, to default on payment, there's a calculated risk in giving credit to consumers, right? So the idea is that we can model the time until default. So the number of pay periods before a debtor defaults on their payments using an exponential distribution. So to clarify, an exponential distribution is a distribution for a continuous random variable. It has a parameter lambda. Where the PDF, the probability density function, is given by lambda times e being Euler's number, to the negative lambda times x, for x being a positive number, or 0, and 0 if it's negative. Okay, so this density curve may look like, if this is 0, and here's 1, and here's 2, might look like this. So I'm using the specific model of an exponential distribution with a lambda equal to 2. Okay, so that would be this curve right here. Everything past 0 is given by the function f of x equals 2 times e to the negative 2x. And so the cumulative density function, the thing that actually gives us probabilities, remember, so if we're looking at areas, right, there's actually closed form for this function where the cumulative density function, the CDF, is given by this function, 1 minus e to the negative lambda x, given x is greater than or equal to 0, and 0 if it's less than 0. So importantly here, you can never actually reach 1. So this function is increasing, right? So you are getting higher and higher probabilities, getting closer and closer to 1, but you never actually get there, okay? So let's say we want to find the probability that a debtor defaults between 1 and 2 payment cycles. So for us, we're working again with x being an exponential distribution with parameter 2. So lambda is 2. So we seek probability that x is between 1 and 2, which, as we discussed before, is the same thing as finding the CDF evaluated at 2 minus the CDF evaluated at 1. And we have this function, so we can just plug in our values. So namely, 1 minus e to the negative 2 times 2 minus 1 minus e to the negative 2 times 1. So if we simplify this, right, so order of operations, make sure you take care of all the negative signs, right? So we have 1 minus e to the negative 4 minus 1 plus e to the negative 2. So you'll notice the 1's cancel here, and we actually end up with e to the negative 2 minus e to the negative 4. And if you evaluate this on a calculator, you'll get the approximation 0.1170. And so this actually corresponds to this part of the distribution. So in other words, we're looking at this area right here. And that's what we just calculated. So that's the probability. We have the function here for the CDF. Frequently, though, a CDF may not have a closed form. Or it's so complicated, closed form meaning it has a formula, or it may be so complicated that it's just impractical. Impractical to use. So what do we do then? Typically, we'll resort to technology, as we'll see in the next few sections. We'll frequently be using technology to find probabilities for continuous random variables, like normal distributions. Or we can use tables, which were, historically what we would use if we were working with these.